Mm-hmm. All right, so are there any questions we wanted to look at on 1-1? I know we had one that was about 8 part something. Which part on 8 were we stuck on? I can't remember which letter. I know it was one of the ones in the middle, like FGHI, somewhere on there. Was it F? F. Okay. Let's look at 8F. Does anyone have any others you want to work through, talk through at this time? And if it comes up later, that's okay too. I'm just sitting because Gen Con was a lot of walking, so I'm a little tired.
I don't have a safe place to put this in my house right now, so I will carry it.
Yeah, put it in your locker.
I don't use my locker.
I didn't say you had to use it, but just put it in there and leave it.
I don't even know where my locker is.
It's on your schedule, the one the school gave you.
I know, but I forgot how to use a locker.
Well, I can tell you that part. All right. So 8F says the negative of M is not less than -2, which feels like English more than math, because it is all about the how many knots are in here kind of vibe. So if we think about this just kind of in pieces, if we say it's not less than, what's another way I can say it's not less than? Greater than, or could it be equal to? So this would be greater than or equal to. So you could say that the negative of M, so M but not positive, negative, is not less than, greater than or equal to, -2. That is absolutely a valid way of writing it. Or if the negatives there kind of bother you, because for some people it does, we go, ugh. To make it all positive, you could put that M has to be, and when we divide by a negative, our inequality sign flips. So M has to be less than or equal to 2. Either way is fine. That works for both of them. So watch out for whatever our inequality is then, and then kind of deal with each side of the statement independently. Because this number 8 is a lot about the words, and like they're all that kind of vibe. I think F is the one that's the most confusing because it has, what, 1, 2, 3 negatives in it? Yeah, it's got 3 negatives in it, and in all different ways. The negative, the not, and the minus. So it just feels a little, I'm not going to the store. So, totally get why that one is a confusing one, 100%, okay? It's all about the weird wording, and this book loves to do weird wording stuff. So feel free, please ask questions, because I don't know what old-timey, old English language translation they used, but sometimes thou hast done math is what it feels like. It's like reading a Shakespearean math textbook. Ew. Okay, so sometimes the book just likes to word things weird, and that's annoying, but a thing that happens, and I don't get to pick the textbook. IU picks the textbook. So, yay, we love it so much. Okay, any other questions from 1-1 at this time? I'm not saying it has to all be right now. Okay. Okay. If more come up, totally valid. Let me know.
Sorry, no work.
Understood. That's okay. We gonna do some review still today. Everything we're gonna do is review. We've seen these before. We're just gonna practice them again. We're gonna talk about radicals today. We're gonna do several things with radicals. We're gonna look at some other kinds of pieces and chunks, just so we can make sure we get all the things we need. Oh, fun. I love when it likes to play with my formatting. That I is definitely not an I. There we go. Getting rid of that piece. There was a random, the word is behind the fractional, or the radical.
Why?
Because Google and Annotate have decided to fight. And they chose violence against me. As is tradition. Kind of like if you look down here, because I haven't covered this one up yet. This radical is supposed to be in the blank here. All right. So I'm just going to draw that guy in here. Again, you do not have to like straight up copy this stuff down if you don't want to. Again, I'm never going to check your notes. I'm just fixing this one. All right. So we're going to be looking at radicals in all kinds of different ways today. So this is a radical expression, and we're going to have different kinds of roots where we have n, which goes in the little nook, and I know it's super small. I'm going to write a big one up over here. So that little one says an n here and an a here. So n is called the index. And that'll tell us whether it's a square root, cube root, fourth root, things like that. And what that means is if it's a square root, we're getting pairs of numbers out. If it's a cube root, we're getting groups of 3 out. If it's a fourth root, we're getting groups of 4 out when we're trying to simplify it. The straight up thing here, this little crook, this is the radical sign. This is the radical, which I'm going to be at the end of the board right there. There we go. Radical. And the number underneath the A here is called the radicand. And then I have, again, just like I had with the old exponent laws, I have the old radical laws, which we may or may not be as familiar with, but they are very, very much related to those exponent laws, which we will see why by the end of the day again, if we don't remember, which is valid. So when we have things that are multiplied under a radical, we can always separate them out. So this first radical law is talking about if I have some radical of a times b, I can make that be radical of a times radical of b and separate them. Sometimes that really helps when we have things like numbers and letters in there to make, okay, all the numbers under one, all the x's under one, all the y's under one, and then just think about them individually. That is a lot of times how I will approach them because it makes my brain much happier to do it that way. Same thing, whereas when we have a product, we can break them up. If we have a quotient, we can break them up. So if I have the square root of a fraction, I can make it be the root of a fraction. I can make it be the root of the numerator and the root of the denominator. And then the third one here, we're really not going to see super frequently. It's going to be rare but occasional. And by the time we get to the end of today, we'll see why the heck this happens. If I have a root inside a root, so a radical inside a radical, what we do is we multiply the indexes. Just like if we have a power of a power, we multiply the powers. If we have a root inside a root, we multiply the roots, the indexes. So we're going to practice working with these a little bit, and then we're going to look at why the heck that happens a little bit. So we're going to practice a couple. I know the right-hand one's not too bad to read. So thinking about how we simplify radicals, as you were like doing these manually by hand, which we are going to have to do sometimes, not tons, but a little. There are several different options when we're trying to do square roots by hand. because that's what this is. If there's not a number right here, our default root is a 2, so this is a square root. And you can either do a full factoring of 28. You can find a perfect square that is inside 28, which is, I think, the fastest way to do it. You could do the birthday cake method. For those of us that remember, that's been a hot minute. That kind of vibes. I think the easiest way to do it is to say, okay, what perfect square is a factor of 28? 4. I can break 28 up into 4 times 7, right? So square root of 28 is the same thing as square root of 4 times 7, which, using those the radical laws we were just looking at, I could do as the square root of 4 times the square root of 7. Well, square root of 4, we know. What's the square root of 4? 2. And does 7 have a square root that's nice and tidy and not super gross? No. So fully simplified, we have 2 root 7. It's decimally and gross to do it by hand, and ew. That gives us an option there. I was like, if you want to do this as like a full factoring and you break it all the way down, 2 times 2 times 7 is our full factors, and pulling out a pair of 2's is how we get our 2 root 7. So a couple of different ways to think about it. I do think that thinking about them in terms of perfect squares is a little easier. So then let's look at the cube root of 8/27. So not only do we have an index of 3, we also have that fraction. So let's break them apart. So we can take this and do the cube root of 8 over the cube root of 27. That's using one of those radical laws that we talked about. When we have a quotient, we can break them apart. What is the cube root of 8? 2. What is the cube root of 27? 3. So that one's just 2/3. We're not going to need to know a ton of cubes off the top of our heads. Usually if we can get up to 5, that's usually plenty, 5 or 6. But as we get closer to needing them for things, we'll talk about those more. Okay? Questions on radicals, because I know we haven't radicaled in a while. Cool. Because what these come from is these come from the fact that you can write radicals as fractional exponents.
Ew.
I know, and that is bizarrely small, and I don't like that. So hang on, I'm going to zoom that in just a smidge. Boop. There we go. Just trying to make it easier to read. All right, so that's just straight up copied out of the book. But these down here, they will be when I'm done filling them in. I post them. I should be able to get our notes posted by the end of 5th period every day. Crossing fingers. So when we have a root of any kind, whatever the index is written as the denominator for the power. So if we have a to the first here with an index of n, because this photocopy is trash, even though it's digital, that's where we're getting this 1 over n. And I don't like that it's sideways either. So we could write this same root here as a to the 1 over n as a fraction. So if you have your a to a power of any kind, whether it's inside or outside, that just goes as your numerator. So if we look at something like this down here, 4 to the power of 3/2, this denominator here, this is our index. So that means we're looking at 4 inside a square root, because our index is 2. You can put the 2 or you don't have to. And you can think about this being cubed out here. Or you can do the same thing where we have our square root of our 4, and you can cube it in here. It does not matter. It's kind of like, again, how 2 times 3 is the same thing as 3 times 2. These are both parts of exponential pieces, so I can do it in whatever order. And there's going to be times when doing them in one order or the other is going to be easier. And there's not a shortcut for telling on which one that is. On this one, it's a little easier to see because, do we know 4 cubed off the top of our heads? Mm-hmm. As I say, it's 64. So then we could do that and write this as the square root of 64. What is the square root of 64? 8. Or we can do it on this side and do our square root first. What is the square root of 4? 2. And then 2 cubed? 8. So it doesn't matter what order we do it in. Either way, we're getting the same answer. So if it helps to, that's not the laser pointer. If it helps to square root it first, do that. If you can't square root it, try doing our other exponent first. Like, this is totally fine. Okay, we're going to practice a few more of these, taking our fractional exponents and writing as a radical, and then simplifying as much as we can. There we go. So we got 3 of them up here. So we've got 9 to the 1/2 as our first one. So this tells me the denominator here, that is my index. So this is the same thing as saying 9 with a radical with an index of 2, or the square root of 9. What's square root of 9? 3. I know, I ask such hard questions sometimes. Oh my God. I'm the worst ever. Oh my God. All right, they do get a little harder. So on this one, since I have this numerator in my fraction, that means we're going to have a power in here. And so it might make sense to go one way or the other. So I can either take this and put my 27 inside our cube root and then square it, or I could try and take my 27 and square it and then do the cube root. It doesn't matter which way we go, but I know sure as heck I do not know what 27 squared is off the top of my head. I mean, yeah, we could probably figure it out, but do we know the cube root of 27? Yeah, that's going to be easier. I was going to say, if you know it or if you want to do it that way, valid. Go for it. It'll get you the same answer because then you got to cube root it. Good luck. So we do know the cube root of 27. That one's a bit easier because that's actually just 3. So then we can take our 3 and square it. So our answer is going to be 9. So you don't have to do both ways. You can write it both ways if it helps you. If you start to spot this, great. I love that. If we want to write it both ways and then go, ew, let's try that one. Valid. Okay, so the last one is kind of combining some of our stuff from last week and the stuff we were just talking about with the fractional exponents. So we've got some multiplication, got some stuff going on here. Got some fractional exponents. We got our negative 5a to the 3/2 times 2a to the 1/2. What can we do here? More specific, what do you mean? Oh yeah, to write them both as radicals, you absolutely can do that. 100% totally valid. It is going to actually be easier if we think about these more as exponents and keeping them as fractions for a minute. Because are these parentheses actually doing anything for me here? They're multiplying here. But these are also multiplying. So it doesn't matter what order we multiply things in? Nope. So let's reorder this. Let me put my numbers together. And I'm going to use dark numbers here. So we're going to have our minus 5 times 2. And then we've got our times a to the 3/2 times a to the 1/2. Negative 5 times 2, that we can do. What's negative 5 times 2? Negative 10. When we have exponential pieces where we're multiplying the bases, what do we do with those exponents? Add them. What is 3/2 plus 1/2? 4/2. I was going to say, can we simplify 4/2? Yeah. What is that? 10. 2, because I'm about to write 10, and I said it out loud. 4 divided by 2 gives me 2. So we no longer have a radical in there. So sometimes leaving them as fractional exponents or even taking radicals to make fractional exponents in here makes things simpler because exponent laws are a lot more familiar sometimes than radical laws. But all we had to do was add these two exponents together and then we can simplify down here. Okay? Questions on these three? Because I know we went light, medium, whoa. But that's okay. We can do that. Oh, I love when I accidentally duplicate pages. Can you go away? Thank you. There we go. Okay. Question on these? All right. Because the next thing we're going to do is we're going to talk about radicals and when we have radicals in fractions, fixing that because it gets icky. So this is going to be a thing that we actually do a lot in here because we are going to wind up with times where we have answers that look like this when we're done solving something, where we have a radical in the denominator. And this is actually incredibly bad math grammar. We are not supposed to have radicals in denominators. So if we wind up with a radical in the denominator, we need to do something called rationalizing. And what that means is we're going to take whatever our piece is that has a radical in the denominator, and we need to multiply it by 1. But we're going to pick a really weird looking 1 in order to make my denominator not be a radical, because ew. So this little chart is in your book. I just stole it from there, but I feel like it's going to be easier if we just kind of talk through it down here. Because I want to multiply this by something that's going to equal 1, so it needs to be the same top and bottom, that's going to make this square root of 5 not be a square root of 5 anymore. I want this to be an actual whole number. So what I'm going to multiply it by is actually whatever our radical is, square root of 5, but I need this to be a 1 because I cannot change my expression just because I don't like it. But I can multiply by 1 anytime I want. So as long as it's the same numerator and denominator, it's still 1. It's just a really crazy looking 1. And what happens when we multiply by square root of 5 over square root of 5, multiplying fractions means we multiply across. So we get 1 times square root of 5, which is square root of 5, over square root of 5 times square root of 5, also known as square root of 5 squared. What is square root of 5 squared? 5. So this becomes, changing colors, square root of 5 over 5. Now our denominator does not have a radical in it, so this is technically a better answer than this. There we go. Laser pointer? What is in your mouth? There we go. This is technically a better answer than this. They mean the same thing. And in fact, if I pull up my calculator and I type those in and we look at the decimals, they are 100% exactly the same thing. Ooh, fun. There we go. But this is how we're going to format our answers. We're not going to leave radicals in the denominator. So whatever is your radical, we need to multiply it by something that's going to make it be a whole number. So when we have square roots, we multiply by exactly what it is because we want to square it. If we have something like a cube root, I can't just multiply by 1 root of x because that's not going to get me there. I need to get this up to be 3 because I need a cube here. So on this one, we need to multiply it by 1. So if we have 1 over the cube root of x here, I want to get this cube root of x to have 3 things. So I don't want to multiply it by just x, because that'll only give me 2, and that's still not going to be better. But if I take this to be x squared, but again, I need this to be a funky looking 1, x squared. Now when we multiply these together, if I look at my denominator here, let's look. So if I have my cube root, and we have x times x squared, like that. Now do we see what's happening? Now it's going to be x cubed. So we have the cube root of x cubed, which means we're going to have our denominator be what? What is the cube root of x cubed? Just x. So our numerator up here, we have our 1 times our cube root of x squared. So that's being just cube root of x squared, cube root of x squared. And so our final numerator is our cube root of x squared. We are not going to have to rationalize cubes super frequently. Like, that's kind of a just this chapter situation. But we will have to rationalize square roots a bunch. Bunch of cruncha. All year. Through May. We will be rationalizing things. I think there's only one section where we don't rationalize. So we're going to practice this a couple of times. Several times. Eyes on time. Oh, we are going to love it. So let's practice this a couple of times. So if we have the square root of 2/3, and sometimes it helps to split them apart. So I'm going to take my square root of 2/3. Again, if I ever am going too fast, please, please, please let me know. Square root of 2 over square root of 3. It means the exact same thing, but this lets me see them as separate pieces so that I can figure out what the heck I'm multiplying by to make my denominator be way less gross. Because our denominator being the square root of 3 is not acceptable. So we need to multiply it by a 1, but it's going to be a really funky looking 1. So what are we going to multiply, or what are we going to have as our pieces in our 1? Square root of 3. Because if I multiply by square root of 3, we're going to have in our denominator here, square root of 3 squared. Oh, that's tiny. Hang on. Ah. Squared. And our numerator, we've got square root of 2 times 3. And since they're both in radicals with that same index, we can combine them together. So when we simplify this, what's our numerator going to be? Square root of 6. So we're going to have our square root of 6. And what's our denominator going to be? 3. Can I simplify between the 6 and the 3? No. Please don't. If it's inside a radical, it cannot simplify with the denominator unless that is also inside a radical. So please, please, please don't come here and then go, oh, wait, it's just going to be square root of 2. Ah. No. If I ever show you guys an example like that, that means it's something that people do a lot and it gets in here a little weird. Oh, I'm almost out of coffee. Okay, so now let's do kind of a slightly wilder one. Now we've got a fifth root of x over y squared. Ew, but that's okay, we can do it. So I'm going to break this up into separate pieces again. So I'm going to have my fifth root of x over my fifth root of y squared. If you want to put those as fractional indexes, that is definitely a way to approach it. I'm going to leave them as roots because I don't want to. So, the white's okay. But that what we need to do is we need to figure out what we're going to multiply this by in order to make my denominator not have a root. How many more y's do we need to make this be something we can take a fifth root of? 3. So we're going to multiply this by the fifth root of y cubed. Because I need 3 more y's to make this be rootable. And whatever I'm multiplying by, it's the same numerator and denominator. Because I cannot change my expression, I can just multiply it by a really weird looking 1. And that is a very weird looking 1. So what we're going to have is we have our fraction. I've got my numerator, which has my fifth root of x. And since they had that same index, I can multiply them together. X times y cubed. What's my denominator going to be? It's just going to be a y. And if you need to do that in 2 steps, that's totally valid. So if we write this as fifth root of y to the fifth and then get to our final answer, that is 100% valid. If you can do that jump, I am okay with you making that jump and not writing the step down. Okay? So our final answer on this is going to be our fraction that has the fifth root. Okay, that's a little chunky even for me. There we go. So our fifth root of xy cubed over y. And that's our answer. Okay. Questions on these two? Okay. Fun. I like when I make up problems for myself and I have no idea what the answer is. Wait. All right, we're going to do 2 more. We'll finish out here. This will be the end. Okay, last 2. So we've got the square root of 9x to the negative 4y to the 6th. And we've got fourth root of chaos.
That's my brain.
It happens. And there are a few different ways I can see to approach this left one for sure. You could switch them to be fraction indexes and then simplify, and that'll totally work. But what I'm going to notice first is we've got this minus exponent in here. What happens with a negative exponent? And that becomes our denominator, right? So this is the same thing as saying our square root of 9y to the 6th over x to the 4th, like that. But I don't like to do it as a big square root like that. Let's break this up into numerator and denominators. We're going to have our 9y to the 6th in the square root over the square root of x to the 4th. Do we need to rationalize or can we simplify this out? Let's see what happens when we simplify. In our numerator, what is the square root of 9? Woohoo! What is the square root of y to the 6th? Y to the 3rd. If you think about that as a fractional index, it's the same thing as saying y to the 6, and we had that square root, so it's over 2. There we go. How about our denominator here, x to the 4th under the square root? It's going to be x to the what? X squared. Because radicals and exponents are very much similar, like how addition and subtraction are similar, or multiplication and division are similar. Radicals and exponents are related that way. All right, so then the one on the right, we've got the fourth root of 5x to the 8th y cubed over 27x squared. So first thing I'm going to do is I'm going to split my fraction up into two separate roots. So our numerator, we've got the fourth root of 5x to the 8th y to the 3rd. And our fourth root of 27x squared. What do we notice? Either here or in the first step. What about the x to the 8th? Yeah. Yeah, I've got x's, both numerator and denominator. So I have 8 x's up here and 2 down here. So they're actually going to cancel out. And whether you do that up in this step or if you get down here and notice it, that's totally fine. We're going to wind up with, simplifying that bit out, we've got our fourth root. Oh, that purple hurts to see on the green. That is just painfully sharp. There we go. Fourth root of 5x to the 6th y cubed over our fourth root of 27. That's totally valid. What do we know about 27? It's not a perfect fourth, but what is 27? A perfect cube, perfect third. So I could rewrite 27, and this is going to help us see something here, right here, as, oh, I just picked the purple again and just said that one is like aggressively, it's like looking at a magic eye poster. It's hard to see on this one. If I rewrite this as the fourth root of, instead of putting 27, I put 3 cubed. And then our numerators staying the same for now. 5x to the 6th, y to the 3rd. Now I don't have anything I can simplify in my denominator. What do I need to multiply it by to be able to rationalize this and get something that is fourth rootable? Three to the first. I already have 3 3s. I only need one more. So if we multiply it by the fourth root of 3, that's going to give me just a 3 on the bottom. I'm going to change my view real quick. Hang on, I'm going to make the screen jump for a second. There we go. Just because I need a little more space. So we can take and put our fourth root of 5 times x to the 6th times y to the 3rd times 3 over our fourth root of 3 to the 3rd times 3. We are choosing this value. Like, this is something we get to pick. There's not one right answer. You could put 27 to the 3rd. You're just going to wind up with more simplification to do at the end. What that gives us is that gives us our denominator, fourth root of 3 to the 4th, essentially there is just 3. And then we've got our fourth root. Simplifying our numerator here, 5 times 3 gives us 15. X to the 6th, y to the 3rd. And there's one last thing we can simplify. Does anybody see it? The x. I can take the fourth root of x to the 6th. If I take out a piece here, because I can take one set of x's out, how many x's are we going to have left inside our radical? 2. So we're going to have our 15 x squared y cubed over 3. So it's a mess, and I know it's going to be very small once I write it out, but that would be our simplified answer. I know it does not look better. There will be a lot of times when things do not look better, but our denominator does not have a radical. That's what we want. Okay? So I'm going to put up our announcement page. Homework 1-1 is due tomorrow, so make sure you're working on that. Here's the numbers for homework 1-2. That is over the exponents and the radicals and rationalization. And then tomorrow we're going to start looking at some polynomials funness. And we'll touch on the radicals just a smidge more. Just to confirm, because Miss Bolland asked me to put this up again. If you did not do this QR code on Friday, please do so now, because she needs it to be able to get you into the IU system. So if you did not do this QR code, please do it. I can put it back up here, no problem. I'm putting up homework 1, 2, so that you can see that. Have a great rest of your day. Happy Monday. See you tomorrow. Bye.